this. And if we don't write it as the square, we get velocity over GL square root, where G is a gravitational constant and L is some length scale. But this is for surface flows, so on the surface of the ocean or in a river, wave activity, and open channel flow. The hydraulic jump. And here L denotes the depth of liquid. I'll say water, but it depends upon the fluid that you're dealing with. So that's the Freud number. Another one, the Weber number. This is something that we use if we're dealing with bubbles or meniscus. And it is inertia forces to surface tension. And it has a symbol capital W little e rho v squared L over sigma for surface tension. So you'd use this for droplets. You could use it for bubbles. A droplet would be if you have a liquid in a continuous phase of gas. Bubbles would be if you have a continuous phase of liquid with a dispersed phase of a gas. Meniscus, etc. So there are other applications. And another one that we'll look at, the one that is involved with compressible flow, is the Mach number. And this is inertia forces to compressibility forces. And here the Mach number, quite often we'll see it expressed as V over C. V would be the local velocity and C is the speed of sound at those conditions. And the place where that is coming from goes back to our definition for the speed of sound in gases or in a fluid. And we have the bulk modulus, which is EV. That is our bulk modulus. So that's one way of coming up with the Mach number. Another one, we can write just the ratio of the forces that we're looking at here. So that would be a ratio of inertia to our compressibility forces, and from that the L's would cancel out. We basically get the same sort of relationship that we've just derived in the previous equation. So that is the Mach number. As you approach Mach 1, that's when you get to the sonic condition, and a lot of interesting things happen when you get to Mach 1. You can get shocks, expansion waves, all kinds of things going on. And that is compressible flow, which we will not study in this course. It would be in a more advanced fluid mechanics course. Struhl number. This is for flows wherever you have some sort of natural frequency occurring. If you recall back to a very, very early video of why study fluid mechanics, I had the cavity modes of the Ford Fusion vehicle car. And the cavity mode was caused by vortex shedding off the front of the window. And you would have been able to calculate some sort of Struhl number, probably based on momentum thickness of the shear layer on that window. But Struhl number is used in a lot of different flows where you have instabilities, oscillations, and it is given the symbol ST, and it would be the frequency of that oscillation, some characteristic scale divided by some characteristic velocity. And so this is often an oscillating flow. An example of this that is well studied is the wake behind a cylinder. If you ever follow behind a semi-trailer truck on the highway, what's happening is we have large-scale vertical structures coming off, and that is oscillating, so the vehicle is moving in that direction. That's why your car, as you try to pass one of these big vehicles, you feel it pulling left to right. and you get instabilities as you drive through this wake, and then as you get by, you get cleaner air when you get up and along parallel. So that is a Struhl number. Drag coefficient. And here we have drag force divided by inertia. And we're going to introduce one of those 1/2, just like we did with the pressure coefficient. We do this for a lot of the coefficients: lift coefficient, drag coefficient, pressure coefficient. But what we do is we take the force itself, and this is one that we studied earlier on when we looked at Buckingham pi, but you get 1/2. You get the dynamic pressure in the denominator. So 1/2 rho, some characteristic velocity squared times some projected area. And this would characterize things like drag on bodies. Okay, so those are a lot of the different non-dimensional numbers that are important and used. We can have lift coefficients as well, like drag coefficient, but those are things that we use when we do experiments. And so it enables us to be able to collapse the data, to understand the processes that are occurring, and to be able to scale the data such that other people can use it in their investigations or for engineering design purposes. And that's usually what we're doing as engineers. So experimental fluid mechanicists go in and they conduct these experiments, they create curves, and those are used by design engineers then when they're going through and doing the design for whatever system they are designing. And so those are non-dimensional numbers.